In this video, we're going to have a look at quadrilaterals in analytical geometry. In the Euclidean geometry chapter, we already had an in-depth look at the properties of quadrilaterals, and you're welcome to have a look at that again. The link for that is in the description. Now we're going to have a look at how we can use these properties in analytical geometry. Example 1. In the diagram is a rhombus ABCD with E the point of intersection of the diagonals. First question, determine the value of A. Looking at the sketch, you'll see that the only two full coordinates given is point C, one of the vertices of our rhombus, and point E, the point of intersection of the diagonals. And that is why we're going to use the property of the diagonals of a rhombus to solve the value of A. We know that the diagonals of a rhombus bisect each other, but we don't have the coordinates of B and therefore can't use this property. We also know that the diagonals intersect at 90 degrees, and this we can use. I'm going to start off by determining the gradient of line EC. Now we also know that EC is perpendicular to DE. Therefore, we can say that the gradient of DE will have to be the opposite sign, and that means that this will be positive, and it will be the reciprocal of the gradient of CE, which means it will be a half. Now we can make use of the fact that the gradient of DE is a half and substitute in the coordinates that we were given. The y value of D is A, and we're going to subtract that of E and divide that by the x of point D minus the x of point E. But we now also know that the gradient should equal a half. And now we can make use of algebra to solve the value of A. Firstly, I'm going to get rid of the divided by minus 6 by multiplying by 6 on the left-hand side to get minus 6 over 2. This means we have minus 3 is equal to A plus 1, and to get rid of the plus 1, I'm going to subtract 1, so A will be minus 4. Question 2. Calculate the area of triangle CDE. To calculate the area of a triangle, we have the formula half times base times perpendicular height. And in this case, the perpendicular height and base will be the two sides that intersect at 90 degrees, so that is CE and DE. So now we need to determine the length or distance of CE and DE, and for this we have the distance formula. After substitution and simplification, the distance of CE is the root of 5, and DE will be the root of 45. Now we can substitute these two values into our area formula, so we'll have a half multiplied by the root of 5 multiplied by the root of 45, and now the area will be 7,5 units squared. Next up, we're going to have a look at how to prove quadrilaterals, and first up is the parallelogram. We already had a look at all 5 possibilities in Euclidean geometry. Now let's have a look at how we will apply them in analytical geometry. To prove that both pairs of opposite sides are parallel, we will have to do the gradient formula 4 times. Or, to prove that both pairs of opposite sides are equal, we'll have to make use of the distance formula 4 times. To combine these options and prove that one pair of opposite sides are parallel and equal, we will use 2 gradient and 2 distance formulas. We will only have a look at determining angle sizes in grade 11 analytical geometry, and therefore we cannot yet prove that both pairs of opposite angles are equal. And finally, we can prove that the diagonals bisect each other by determining the midpoint of both diagonals. I'm sure you will agree with me that the quickest way to prove that a quadrilateral is a parallelogram is to prove that the diagonals bisect each other. Next up, to prove that a quadrilateral is a rhombus, you firstly need to know that it is a parallelogram. Then you have the choice of either proving that one pair of adjacent sides are equal, which means we'll have to do the distance formula twice, or you can choose to prove that the diagonals intersect at 90 degrees, which means we'll have to determine two gradients. Moving on to proving that a quadrilateral is a rectangle, we first need to once again know that it's a parallelogram, and then we can choose to either prove that one angle is 90 degrees, which means we'll have to know the gradient of two of the sides. Or you can choose to prove that the diagonals are equal, which means you'll have to determine two distances. Lastly, to prove that a quadrilateral is a square, you need to be able to prove that it's a parallelogram, and then prove one of the properties of a rhombus, as well as one of the properties of a rectangle. Let's go and have a look at an example. Example 2. Quadrilateral KLMN is given. First question, prove that KLMN is a parallelogram. Earlier I mentioned that the quickest way to prove that a quadrilateral is a parallelogram is to prove that the diagonals' midpoints are at the same point. Therefore, I'm going to start by determining the midpoint of NL using the midpoint formula. And here you will find that the midpoint of NL has the coordinate 1/2 and 4.5. Now I'm also going to calculate the coordinate of the midpoint of KM, and this will also work out to be 1/2 and 4.5. Now we can make the conclusion that KLMN is a parallelogram, and the reason for this will be that the diagonals bisect each other. Question 2. Prove that KLMN is also a rectangle. In this case, I'm going to choose to prove that one of the angles is 90 degrees. And for that, I'm going to determine the gradient of NK and the gradient of KL. The gradient of NK can be determined using the gradient formula. And this will work out to be -3/2. Next up, the gradient of KL will then be 2/3. If I now go and determine the product of gradient NK and gradient KL, it will be -3/2 times 2/3, and this is -1. From this, we now know that NK is perpendicular to KL, and we can then make the conclusion that angle K is 90 degrees. And therefore KLMN is also a rectangle because it's a parallelogram with a 90-degree angle.